Hello, everyone. Thank you so much to the organizers for giving me the opportunity to present this work here today. My name is Juan Mena. I'm a postdoc at LPSC in Grenoble in France. And today, I will talk about one of the latest analyses that we did in the dark energy survey, which is about basically combining the latest dark energy survey, Baryonic Acoustic Oscillations at type 1a supernovae to constrain cosmological parameters, in particular dynamical dark energy. So first I will say a few words about the dark energy survey. The DES is a photometric galaxy survey that took data in the 5 different bands in the optical and near infrared. So DES has 2 distinct surveys. First we have the wide survey, which lasted from for 6 years, during 2013 and 2019. It covered around 5,000 square degrees with a depth in the eye magnitude band of around 23.8. And we had more than 1 million galaxies with shapes and photometric redshifts up to redshift of around 1.4. On the other hand, we have the supernova survey, for which this one, instead of 6 years, it was 5 years with 6-month seasons. And we had 10 supernova fields with a total of 30 square degrees. Here you can see the footprint of the dark energy survey. The white field is the red kind of tank. And then the supernova fields are the 10 small points here. And this is the galactic plane, so the entirety of the DES footprint is in the south galactic cap. So the main goal of DES is to try to unveil the nature of dark energy. And in order to do so, we have 2 different kinds of dark energy probes. First, we have the ones that help us studying the expansion history of the universe, so meaning the background evolution of the universe. And we have 2 different probes. We have the measurement of the Baryonic Acoustic Oscillation scale from the galaxy clustering signal and the type 1f supernovae. On the other hand, we have probes that allow us to study the structural growth, so the evolution of the primordial density fluctuations of the universe. And here we have 3 different probes. We have the full shape of the galaxy clustering. Here we are just focusing on the BO scale. Here we're using the entirety of the galaxy clustering signal. And weak lensing, the combination of these 2 is what we refer to usually as 3 times 2 PT. And this analysis is ongoing right now for the GR6 dataset, so stay tuned for the results. And galaxy clusters. But what we're going to focus on this talk, as I said before, is the combination of the expansion history probes, Baryonic Acoustic Oscillations, and type 1a supernovae. So these results are already out since 1 year ago, and these are the final type 1a supernovae results. We already published them. Credits to Jesse for these wonderful plots. So both type 1a supernovae and BAO are distance probes. First, type 1a supernovae, because of the uniform luminosity at peak, they're used as standardizable candles, and they basically allow us to measure the luminosity distance as a function of redshift, which depends on cosmological parameters because it depends on the Hubble parameter, h of c. On the other hand, the BAO, basically what we have is the sound horizon scale imprinted in the galaxy clustering signal, and this is used as a standard ruler to measure distances. And basically with the BAO, we have access to the angular diameter distance, co-moving angular diameter distance as a function of redshift. And this depends on cosmology again, because it depends on the Hubble parameter, that it depends on the Hubble constant and the different density contributions. And these 2 are related by a factor 1 plus redshift. So part of the motivation why we did this analysis in DES is because of everything that happened in 2024. So first thing that I wanted to highlight is in January, we released the latest dark energy survey supernova results, and meaning the 5 years of supernova survey. And we found a 2 sigma preference for W0 WA cosmology, or 2 sigma tension with Lambda CDM. Here you can see the W0 WA plane, and this is where Lambda CDM would lie in a W0 not -1, WA0. And this is a result that we found from purely supernovae, the blue one, which is almost in a 2 sigma tension with Lambda CDM. Then in February, we released the latest dark energy survey BAO results. And what we found is a 2.1 sigma tension with blank Lambda CDM prediction. So basically, this was telling us that maybe interpreting our results like both BAO and CMB under Lambda CDM was going to be complicated. And then, of course, in DESI, we released the DESI data release 1 results, or 2024 BAO results. And when combining with CMB and type 1a supernovae, same supernovae that we released in DES 3 months before, we found a 3.9 sigma preference for W0 WA, which was already pointing towards something. So basically, our motivation for this analysis is doing something similar to what we did in DESI, but instead of using DESI BAO, use DES BAO, meaning Baryonic Acoustic Oscillations from a photometric survey. So yeah, the focus of this talk is the combination of these two again. A little bit of a highlight of some of the main aspects of the DES DR5 supernova analysis. So this is the DES supernova team. So because of the work of all these people, this was possible, of course. The DES Y5 supernova sample is the largest and deepest supernova sample from a single telescope ever. It has around 1,600 photometrically classified type 1a supernovae, with calibrated to 5 millimagnitude accuracy, and with spectra for host galaxy redshifts. For cosmology, we combine our DES supernova sample with data from around 200 low redshift supernovae from a compilation of historical supernovae. Basically, what we measure is that calibrated distance modulus that depends on the measured magnitude, on the supernova intrinsic magnitude, which is degenerated with H0, and unless supernovae are calibrated, we don't have access to this number. And then it also depends on the calibration, like supernova color, stretch, and all the stuff. And this thing is proportional to the luminosity distance as a function of redshift, as I said before. Here you can see the distance modulus as a function of redshift for the DES supernovae in blue here, and the probability of them being a type 1a supernovae. And also the low redshift sample, which again, as I said, is a compilation of other supernova surveys. And this is the data that we're going to be using in this study here. Then talking about the DES DR6 BAO analysis, again, this is the latest DES BAO analysis. And then the last one, there will not be another one. This is the team that made this analysis possible. So just some highlights. So for this analysis, we optimized the sample for the measurement of BAO. And in the end, we had a sample with around 16 million bright galaxies over around 4,200 square degrees in 6 tomographic bins from 0.6 to 1.2, meaning separated by delta C 0.1. We measure the BAO signal with 3 different clustering statistics, and then we combine them all, taking into account their covariance from simulations, estimated from simulations. And we found a 3.5 significance detection of the BAO peak. We run BAO fits kind of similar to what we do in DESI, with a template-based method. We validated the analysis using 2,000 mock catalogs, almost 2,000 mock catalogs. We run lots of robustness tests and also lots of pre-unblinding tests because we run this analysis blinded. And in the end, we had a consensus likelihood as a function of alpha, which is none other than the comoving angular diameter distance at the effective redshift of our BAO sample, which is around 0.85, rescaled with the sound horizon scale here. And this same quantity in the denominator evaluated at the cosmological parameters of the template, which in this case was blank 2018. And again, we from BAO, we measure, from angular BAO, we measure the comoving angular diameter distance. And this is just a plot showing the angular correlation function as a function of redshift from high to low redshift. And you can see how, for example, the BAO peak moves to larger to smaller angular scales as redshift decreases because of its constant comoving size. And this is one of the 3 clustering statistics that we used, and we combined the 3 of them. This is just one of them as an example. And in this analysis, this combined the BAO plus supernova analysis. This is the team that mainly participated on it. So what we're going to have, as I said, on the BAO side, it's a DES-06 BAO or supernova. We have the DES-05 supernova. And then we're also going to use external data. In particular, data from the cosmic microwave background from Bang 2018, the temperature and polarization power spectra. And theta stars, sometimes when we don't want to use the entire CMB information, we will be using this angular scale of the acoustic peak. And we will also be using a prior on small omega b from Big Bang Nucleosynthesis as well, as you will see later. And these are basically the DES dataset that we're going to be using here. So meaning the blue ones are the supernovae, and the red one is the BAO that we're going to be using now. So all that said, now we'll show you the main results, basically constraints on cosmological parameters from this analysis. First, I will start in Lambda CDM, and then we will move to extended models. So in Lambda CDM, first, what we usually hear is the Hubble constant and omega m. And this green contour here is the combination of BAO, BBN, and theta star. So when we combine the 3 of them, we can already constrain quite well, relatively well, H0 and omega matter. And what you can see is that there is a tension with the results from supernovae. Again, BAO here means DES BAO, and supernova means DES supernova. So there is a tension here in Lambda CDM, as you can see. If we combine, for example, BAO plus supernova plus BBN, we get the gray contour here, which prefers a higher value for H0. And if we switch BBN with theta star, we get the yellow one, which prefers a lower value for H0. Also in clear tension between them. So basically, in Lambda CDM, we find several 2-3 sigma tensions between different datasets. So we have difficulties to interpret out different datasets within Lambda CDM. Here in black, I'm showing the CMB. With a CMB is very constraining in Lambda CDM by itself. However, if we add our BAO, that's going to move the CMB constraints to larger values of H0, lower values of omega matter. And on the other hand, if we include type 1a supernovae, that's going to be on the other direction. So basically, BAO and supernovae are pushing the contours to different directions in the parameter space, which is one of the reasons why we move to extended models. And the first one we're going to try is K lambda CDM, meaning that we allow the curvature to vary, to be different from 0. This dashed line would be flat, meaning omega k equals 0. And here you can see, for example, the results for CMB and the results from the combination of all geometric probes, meaning BAO, supernovae, BBN, and theta star. And you can see that these two are in clear tension. Here I'm also showing some other results. For example, combining BAO plus CMB, it's moving the result to flatness. It's consistent with flatness. However, when combining with supernova instead, that's still in tension with flatness. Yeah, all this to say that we find kind of similar results to what we find in Lambda CDM, meaning that we have difficulties interpreting our results, our different datasets, also when allowing the curvature to be different from 0. Here you can see, for example, purple prefers quite a positive value for omega k, whereas CMB by itself prefers a -1. So now we're going to move to a different one-parameter extension for WCDM, in which we allow the equation of state parameter for dark energy to be different from -1. -1 would be here, that is Lambda CDM. And you can see kind of the same story that we saw before in Lambda CDM and K lambda CDM. And it's that if you compare, for example, the result for supernova with the result from the combination of BAO and CMB, the red one, they are in clear tension, and it's actually a tension of around 2.5 sigma. Our most constraining case is a combination of Ia Supernova and CMB, even though we're combining two things that are a little bit inconsistent, but we are aware of that. And we find that this result is consistent with Lambda CDM, but again, we are combining things that are in clear tension. So we find similar results to Lambda CDM and K Lambda CDM in the sense that Ia and Supernova are still pushing in different directions of the parameter space. So now we're going to move to W0 WA. We will have one more extra parameter compared to these one parameter extensions. So what we find in W0 WA, we're going to be assuming the CPL parameterization. So all the plots I will show now, I believe all of them are simply in the W0 WA plane. What we find in W0 WA is that all our probes are compatible. And when I say they are compatible, I not only mean that they are compatible in W0 WA, but they are compatible in the entire parameter space, not only dark energy-wise. Our main constraint is the combination of BAO, Supernova, and CMB. And we find a 3.2 sigma deviation from Lambda CDM. That will be the orange one here. That's our main result. We also show, in this slide, I also show results from background-only probes, which are a combination of BAO, Supernova, BBN and theta star, meaning like substituting CMB with BBN and theta star. And even though the constraining power is worse, we still find a significant tension with Lambda CDM of 2.8 sigma. And it's the purple one here. We also kind of reanalyzed the DESI data release 1 results. Basically, the pink, well, red, pink here is the same as the orange one, but substituting our BAO with DESI DR1 BAO. And you can see that it is quite consistent, even though, of course, with using the DESI BAO, the constraining power is higher. But the results are still very consistent between them, and we found a 3.6 sigma deviation from Lambda CDM, which is consistent with the DESI fiducial analysis. So just to summarize a little bit, this is our baseline result, which is, again, the combination of BAO, Supernova, and CMB. Again, this is the final DES BAO and Supernova analysis. That's why we wanted to do this, to have like a view of what DES can tell about the expansion history. And our result is a 3.2 sigma deviation from Lambda CDM. In this plot, I'm also showing the 3 sigma contour. And if we do similarly to what DESI does, and we quote the sigmas from the delta chi-squared of the maximum a posteriori between the two chains, we get around 2.7 sigma preference for W0 WA, which is consistent with our tension metric. Conclusions. Again, these cosmology results from DES, BAO, and Supernova represent the culmination of what the completed dark energy survey can tell us about the expansion history of the universe via geometric probes. And this work is possible thanks to a lot of people working on DES. In Lambda CDM and one parameter extensions that we considered, we saw that BAO tends to pull constraints to go towards lower values of omega matter, and Supernova towards higher values of omega matter, and we found 2.3 or 2-3 sigma tensions between data combinations. We found that all datasets are compatible in W0 WA, which is great. We're able to interpret all of them in this model, and we found a 3 sigma preference for W0 WA. And that's it. Thank you so much for your attention.
Thanks for a very nice talk. So we have plenty of time for questions. So any questions? Leandros?
Okay, thanks for the nice talk. I'd like to ask about the one subject we didn't mention in your talk, only the beginning, where you had these 3 plots, three images about the growth tension. Can you, of course, we heard from the kids' talk that the growth tension has disappeared according to their analysis. Here you have three probes, galaxy clustering, weak lensing, and galaxy clusters. Can you comment on the level of growth tension that you see through these probes so far?
You mean the level of...
The S8 tension, does it remain according to your data, or is it much weaker, as we heard from the kids' data?
Sorry, but you mean what do I expect from the final analysis?
What do your data so far show in terms of the growth tension? I mean, I guess this data exists already. You have the data. I mean, you know the data.
We have this analysis is for the year 3 is already out.
Yeah. Okay.
3 years ago, I believe.
Okay.
For the year 6, it's ongoing.
You have nothing to say about that?
No. It's blinded, actually. We are running the pre-unblinding tests at the moment for the year 6 analysis of the DES. So I cannot say anything about that, actually.
I see.
But it will be, like, hopefully, always hopefully, it will be finished relatively soon, this analysis. And it's very exciting because we will be able to see if we find an SI tension or sigma tension or not from the DES.
Okay, thank you.
Any other questions?
Thank you for a nice talk. I'm wondering, do you think there are other possibilities can alleviate the omega M and H0 tension except for omega W0WA?
Sorry, you mean that other possibilities can?
Can alleviate the tension.
The tension between?
Between BAO and supernova.
So from our study, among the models that we tried.
Yeah. Because you say that in your data, your BAO and supernova data have tensions in omega M and H0.
Yes.
And I'm just wondering, do you think there are other possibilities except for W0WA that can resolve the tension?
Like other models or other stuff?
Yeah. Is there any other possibilities, or do you think it is?
I guess so. Yes, but we have not like studied our possibilities besides the ones that I presented here today.
Yeah, I know. So in your mind, do you have any ideas that there is any other possibilities?
I don't know. I guess I don't have any in mind right now. But I guess like some other stuff could help alleviating the tension. You mean like within Lambda CDM or? Or your data analysis method or things like that? No, I don't think so. Like on the data analysis side or systematic side, I don't think so.
Well, thank you so much to Juan.